Thank you. So it's my pleasure to introduce to you Professor Mustafa Amin. Mustafa received his PhD from Stanford University, followed by Pappalardo Fellowship at MIT, and then Senior Copley Fellowship at University of Cambridge. He's currently an associate professor at Rice University in Houston, Texas. Mustafa's work has covered a wide range of topics in cosmology from early to late universe. In the early universe, I know I've been following his work specifically on reheating and how we can tackle that era, which is something that not everybody dare to do due to messy calculations. Today, however, he will be telling us more about his work on dark matter. So without further ado, I give the floor to you. Please go ahead.
Thanks a lot, Ghazal. Thanks for the invitation, and hopefully this should be fun. So, and please, as I said before, please feel free to interrupt me. If I can get to the point, I might defer questions to later, but otherwise, please do feel free to interrupt. Okay. So what I want to tell you about today is a spin on wave dark matter. Okay, this is kind of a pun, but what I really want to tell you is is it possible that the spin of dark matter can manifest itself on macroscopic or even astrophysical scales? Given that we live in the world of Zoom and limited attention spans and so on, I'm going to first start with a 5-minute summary of what this talk is going to be all about, and then dive into details. What I want to tell you in this talk is that if you start with dark matter, be it a dark matter being a massive scalar field or a vector field or even a tensor field, then when you take the non-relativistic limit of the system, you can describe it by a multi-component Schrödinger-Poisson system. This by itself is already quite useful because, as some of you probably know, in the case of things like fuzzy dark matter, this helps a lot in carrying out cosmological simulations and even giving some detailed analytic understanding of the scalar system. I'm going to show that this also works for higher spin systems. And then I'm going to tell you that these higher spin systems also include an exciting class of objects called solitons. These are localized lumps of energy. And one of the exciting things I'm going to tell you about, which we found, is that many of these objects can have macroscopic intrinsic spin, not orbital angular momentum, but intrinsic spin, which can be proportional to the occupation number in these objects. And the spin aspect can lead to some interesting implications. Time permitting, I'll tell you something about these implications, including things like, what happens to the formation of structure, how these objects, once they form, interact with each other, what their connection will be in terms of their signatures in the electromagnetic spectrum, as well as in terms of gravitational waves. So the first part of the talk will be a bit technical in terms of trying to tell you more about the theoretical framework of this. The second part will be geared towards the implications. Right. So let me start now with a bit of motivation for why we ended up thinking about it. So I don't need to say this to this audience, but we know that dark matter probably exists, but we don't know anything about the mass of this dark matter particle. It could be anywhere between 10 to the minus 22 eV, 20 eV, perhaps all the way up to Planck masses. If it's composite, it can even be bigger. We also don't know anything about the spin of dark matter. We don't know whether it's a scalar, vector, tensor, or a fermion. Now, as I told you, I'm sort of interested in macroscopic or astrophysical effects of spin. So for that reason, I'm going to focus on masses of this dark matter particle, whatever its spin be, which is quite light. By quite light, I mean perhaps something lighter than the QCD axion, which is about 10 to the minus 6 eV, as a result of which the Compton scale would be 10 centimeters. Of course, you could make it fuzzy, and in that case, the Compton scale would be 10 to the 16 centimeters, which is definitely macroscopic and even astrophysical. This is the Compton scale. The de Broglie scale will even be bigger by a factor of 10 to the 3 roughly. Now, another reason I'm focused on small masses is because the occupation number of the fields will be very large for the configurations I'm interested in. So in a heuristic sense, I'll be able to treat these fields classically. And the wave effects and the solitons and stuff that I'm talking about will be natural to describe just in terms of classical fields. I'm also going to focus on bosonic configurations, again, because I can build up occupation number quite easily without worrying about things like Pauli exclusion and so on. So these are my reasons for sort of thinking more about bosonic and light dark matter. Okay, so what kind of models am I going to be thinking about? So specifically, the overarching picture is that I'll be thinking about some spin S field coupled to gravity. And because I'm interested mostly in weak field gravity and in cosmological applications, considering for the most part, apart from the background, quadratic actions for all of these will be sufficient, along with the leading gravitational interaction. This is a sort of a blast slide, but just to lay the framework, if I'm thinking about a spin 0 field, which is a scalar field, I'm just thinking about the Klein-Gordon Lagrangian. If I'm thinking about a spin 1 field, I'm thinking about a Proca Lagrangian. I'm always thinking about real valued fields here, not complex valued ones. So it's a real valued field, massive field. And then in case of spin 2 at the quadratic level, I'm thinking about the Ferris-Pauli action for the massive tensor field. Now, quickly, what I want to do next is take the non-relativistic limit of the system, again, because for the most part, I have dark matter applications in mind. To do this, the first thing we need to do is separate out the physical degrees of freedom. These systems have constraints in them, which can be plugged back appropriately to write down just the action in terms of physical degrees of freedom. Once you do that, for the scalar case, you just have 1 degree of freedom. There are no constraints really. For the spin 1 case, that is a vector field, you have 3 degrees of freedom. And for the spin 2 case, massive spin 2 case, you have 5 degrees of freedom. In general, for spin S, you have 2s plus 1 components. What you do next is you split up this field F, which is a general name I'm giving for a spin S field, physical parts of the spin S field. I'm going to break it up into a slow part and a fast part.
Sorry, Mustafa, we have a
question. Yes, please.
Oh, sorry. Yeah. I was just curious, since you're interested in nonlinear things, what's the justification for using Ferris-Pauli? I mean, that's we're taking it as the complete theory. We're not caring about, large occupation number does not equal strong field. I shouldn't care about the UV completion, yeah. How should I think about that?
Yeah, so this is, Matt, that's a very valid point. And we worried quite a bit, at least in the paper, to think about the difficulties with sort of massive spin 2 fields. But what we have convinced ourselves, and we can talk a lot about this, is that in the regime we are interested in, we are okay. There are large occupation numbers, but the field amplitudes are not so high that we have to worry significantly about nonlinear terms. Moreover, in the non-relativistic limit, there's a fast oscillation that allows you to take away those nonlinear interactions, at least in the leading order. They seem to sort of average out. I'm not giving a detailed answer. So in detail, yes, you have to worry about them. But we can show that in the regime that we are going to be working with, it's okay to ignore that part.
Okay, thanks.
But Matt, we should talk afterwards, because there are subtleties here. There are lots of subtleties especially for the massive spin 2 case that we need to we can discuss more. All right, so continuing on, so we split it into a fast part and a slow part. The fast part is just related to the Compton scale. The slow part is what we are really interested in. So we plug this decomposition back into the action. And we use the non-relativistic limit here, which is to say that the slow part is really slow in the sense that the variation is slow compared to Compton scale, both in space and time. And once you do that, you can write down an effective action for the slow part. Okay? And that effective action is what is written in this gray box right here. This effective action is, if you ignore the gravitational potential phi that appears here, is just the Schrodinger action. Okay? There's nothing else there. The gravitational part is just that this field is interacting by a weak field Newtonian gravity. Okay? So that's what you end up with this exercise. It's a little bit of work to get here, but can be done. And this bold-faced psi that I'm writing here is a general object. If you're thinking of a scalar, it's just a single component object. If you're thinking about spin 1, it's a 3-component object. If you're thinking about spin 2, it's a 5-component object. So this is the non-relativistic effective action. And of course, the corresponding equations of motion are just the Schrodinger equation and the Poisson equation. I want to stress that even though this looks like the Schrodinger equation, we shouldn't interpret the field psi as a wave function, really. It should really be interpreted as part of as a classical field where magnitude psi squared, or more appropriately psi dagger psi, traced over is really the density, okay? The mass density in the field. Okay, so this is what I meant by saying that when you take the non-relativistic limit of these fields, you just get a multi-component Schrodinger-Poisson system. For the scalar field case, this has already been quite useful in carrying out numerical simulations. It's basically because there's a separation of scales here. You're now only caring about scales that are large compared to the Compton scale, and you don't have to resolve the oscillations in the field. So this helps a lot in carrying out numerical simulations, which have been used quite effectively in the past for scalar fields. Recently, there has also been work in just deriving these equations by my former graduate student, Carlo Lozano. In this work, I was not involved in this particular work that he did with Pete Alshed as well, where they did this, we derived the Schrodinger-Poisson system for the vector dark matter case as well. And if you're interested in looking at corrections to this system, at least in the scalar case, there's some references at the bottom as well. Okay, so that's the derivation of the non-relativistic limit. Now let's look at some fun solutions here. These are the polarized solitons that I want to discuss. First, mostly for the students, if you're attending, this is, I use the word soliton without really talking much about what they are. So solitons have a really long history. I often, when I write papers on solitons, I enjoy the fact that I can put the first citation in 1834, which is fun. And solitons arguably were discovered by John Scott Russell. And the story goes that he was riding along a canal near Edinburgh on horseback, and he saw that a barge came to rest in the canal, and it created a pulse, which once created, it traveled pulse in the water, and it traveled without distortion for a couple of miles. And he followed this on horseback till he could follow it no further, and it traveled without dispersion. This, by the way, the picture on this top side is actually the recreation of that soliton in the same canal more recently. As you can see there. So in a very broad sense, solitons are very long-lived dynamical excitation in the field where nonlinearities and dispersion balance each other. Since then, we have experimentally verified the existence of solitons in optics and hydrodynamics in bosons and condensates, and they are also used quite often and appealed to in high energy physics, and particularly relevant for our purposes in cosmology. The types of solitons that I want to talk about are what are called non-topological solitons, which means solitons that don't have some topological feature that allows them to be stable or long-lived. An example of this that is very well studied is just in a scalar field, where it's a localized excitation of the field which just keeps on oscillating without dispersing off. If this excitation is held together by gravity, then usually it's referred to as a scalar star. If it's held together by self-interactions, it's usually referred to as an oscillon. What we want to discuss is sort of a generalization of this when you have a vector or a tensor field. And that's why hence in case for higher spin. And here, initially, I'm mostly going to be, and so far I've mostly focused on talking about these theories where self-interactions have been, attractive self-interactions have been turned off and only gravity is the only thing in the problem. But I'll get to self-interactions as well. Okay, so just a quick recap of the solutions for these solitons. In the non-relativistic limit, these solitons are basically the ground state solutions for a fixed particle number. Their profiles satisfy a Schrodinger equation. It's like an eigenvalue equation that we are familiar with. It's just that here, this external, what you usually think of the external potential now is determined by the field itself. Okay, so it's a Schrodinger-Poisson system. And you can solve this system quite easily. And there's a universal profile that emerges, which can just be scaled by this mu that appears here, which can be thought of as a chemical potential. But there is a nice universal answer for these solitons that can be worked out. We can figure out what the size of this object is, what the occupation number is, what the energy is, quite based on the solution. As long as its chemical potential is small compared to the rest mass m of the particles, then the size of this object is much larger than the Compton scale. So these are, in that sense, these are non-relativistic objects. The occupation number is proportional to the Planck mass squared over the mass of the particle squared again, which again makes it the occupation number very large, which allows you to be quite safe in terms of thinking classically. And the energy is also large compared to energy of an individual quanta, or rest mass energy of the individual quanta, usually. So all, and again, just the total energy is negative, telling you that this object is bound. Okay, so that's sort of the description of a scalar soliton. All you need to do to think about the vector and tensor solitons is to just attach a polarization tensor at the end. Okay, it's the same solution just with this polarization tensor at the end. For the vector case, it's just these two objects that are shown here. For the tensor case, there are these 5 objects which correspond to the spin. And the number of these objects is just the number of spin multiplicities, which is 2s plus 1. Okay, it's the same solutions just with this extra object attached at the end. The results for the particle number remain the same. Energy also, it remains the same. But something new that appears here, which we don't have to think about in terms of scalars, is that suddenly now you have to think about the spin, the total spin of these objects. So we went ahead and calculated the total spin associated with each one of these configurations. For the scalar case, the spin is of course 0. For the vector case, the spin is just proportional to the spin multiplicity times the occupation number. That's all the spin works out, total spin works out to be. So if you are in a state where the spin multiplicity is non-zero, for the vector case or for the tensor case, then you get a macroscopic spin just proportional to the occupation number of these configurations. Again, I want to stress that this is intrinsic spin, not orbital angular momentum. Right? So orbital angular momentum for all of these objects is actually 0.
Can you define intrinsic spin? You mean there's some operator that I apply to this configuration and it has a conserved eigenvalue? Or what do you mean by intrinsic spin?
Okay, so I had hoped somebody would ask the question, and I thanks, Matt, for asking. So what I mean by that is when I write down the angular momentum, sorry, the conserved charge associated with rotations, right, which we can do for relativistic theory. We can split it into the part that looks like usual angular momentum, xt minus tx, where in this case, t is the Noether energy momentum tensor. And then there is an extra piece that's left over. And the extra piece that's left over is what I mean by intrinsic spin. Does that answer? It's in the classical case, I'm just going by I'm defining it in terms of the conserved charge associated with rotation. And there are two parts of this conserved charge, one corresponding to it's a spin, one corresponding to orbital.
Okay, thanks.
So you can define it completely classically. In fact, what we did was you can also just do this directly for the Schrodinger Poisson system and just define, okay, I want to define I have an action I want to define. I have it's invariant in the rotations. I can define, I can just use Noether's theorem to define a conserved charge that way. And you will find that there are two separately conserved things associated with rotation. One is orbital angular momentum, the other one is spin angular momentum.
Thank you.
Okay. But if you're wondering about how this connects to the quantum mechanical aspects of that, what this should be is if you take the expectation value of a spin operator for the state, it should give the same result.
Can you tell me a little bit more? So both are some kind of Noether charms corresponding some contraction of T mu, but one is with like a vector or something. How do you define it again? You said it, but
right. So if you unfortunately I didn't. Let me actually, if you don't mind, I'm going to actually skip a slide. So give me 1 second. I'm going to stop sharing for a moment so I can find my slide. 1 second. Oops, where did my presentation go? Let me share again. Okay. Because can you see this?
yes.
Okay. So this is right now just for the non-relativistic field. I can show you the relativistic version as well. So for the non-relativistic version, so the spin is at the bottom, right? If you can see here, okay, this is the spin density. Is you just take the non-relativistic part of the field, and there's an epsilon ijk attached to it. For a vector field, you can think of it as a cross product between the vector and its time derivative.
I see. Okay.
So it's the vector and its time derivative. It's a similar extension is there. Whereas the orbital part will have a x part with you. It will be x cross something. Okay.
Mm-hmm. Okay. Okay. Thanks.
Okay. Let me continue. Okay. So, all right. So this is fun, right? So there's this intrinsic spin associated with these objects, and it can be macroscopically large, and it's just proportional essentially to the occupation number of these objects. Just for fun, I tried to do a comparison between the spin of these objects and the spin of a Kerr black hole. That's the comparison that's written right here. You can, not surprisingly, you can make the spin of these objects bigger than that of a black hole under appropriate conditions. I don't think there's something really fancy going on there. You can also talk about the intrinsic spin of these objects compared to the spin of dark matter halos. I'm just doing this, I think a more careful study should be done in terms of what comparison should we be making in terms of what we hold fixed and what we don't hold fixed. But one thing I do want to stress is that there's no orbital angular momentum. By the way, for the black hole case, here lambda is just an ordered unity number. Capital M is the mass of these, total mass of the solitons, and little m is the mass of the quanta. And the total mass is proportional to m Planck squared over m, roughly speaking, with a numerical coefficient. So let me just make sure that I'm not, I'm writing down all these expressions in terms of this Schrodinger field, but of course we want to think about this in the context of the real valued vector and tensor fields. So here is just a couple of slides to make sure that we are all on the same page. So the Schrodinger field is psi. I just take the real part of psi times e to the minus imt to construct my actual vector, real valued vector field. Okay? So in that case, my two extremely polarized solitons, meaning what I mean by extremely polarized is that all the quanta have the same polarization. So on the left-hand side is something that is linearly polarized. Okay? So it just looks like at each point, the vector field is moving up and down in one direction. Okay? On the other hand, you could also construct this object in the case of a vector like dark matter that is circularly polarized. So at each location, the vector field is just moving in a circle. And it's this second configuration that has macroscopic spin. The first one has actually zero spin. Okay? So zero total spin, whereas the second one has macroscopic intrinsic spin. So I think this, hopefully, at least for us, this was the most intuitive way of sort of thinking about what's going on. Similarly, we can repeat this exercise for a spin 2 field. For a spin 2 field, you have 3 of these distinct objects, and those are shown here. This time, just for visualization purposes, I have taken what you can see on the bottom, which are the actual solutions for these objects, and I've plotted sort of the eigenvectors scaled by their eigenvalues in the plots above. Okay, of these 6, because otherwise I don't know how to really visualize them in the spin 2 case. So that's what these 3 objects are. And I've suppressed, plus or minus helicity, you can get one from the other by rotation. There's something else you can do here, which in the purely gravitational case and the non-relativistic limit, you can also take linear superpositions of these objects in an appropriate sense, and you can construct fractionally polarized solitons. So those were maximally polarized. Now you can take linear superpositions, and for the same occupation number, you can construct fractionally polarized objects as well. There is one more class of objects which I have not discussed here, which is what has mostly been discussed in the literature when talking about vector dark matter, not dark matter, but just vector solitons or tensor solitons, and those are called these hedgehog configurations. So instead of thinking in terms of these polarization bases, you can imagine, okay, what if I think about it where it's perfectly spherically symmetric, both in terms of the field configuration and energy density configuration? Then you get these hedgehog-like configurations, but it turns out that in the non-relativistic limit, these are higher energy states typically than high energy states than the other ones that I considered. However, there should be, I have to urge some caution that these objects tend to become relativistic towards their cores. So you have to be a little bit careful about the non-relativistic limit here. But nevertheless, it's likely that these objects are, very likely these objects in the non-relativistic limit are certainly high energy. In the relativistic case, I'm not sure which way it will go. Okay, so I want to pause here a bit before I talk about implications. First, Ghazal, let me ask you, how much time do I have left?
Well, technically 28 minutes, but leave 8 minutes for question and answer maybe.
Okay, that's more than enough time. Perfect. Okay. So let me pause. If anybody has questions, please feel free to ask, because now I'm going to sort of switch gears a bit and mostly show pretty pictures and talk about possible implications.
Feel free to turn off your microphone if you have a question. Sounds like
so if these objects were not in isolation though, right, can I still think of this intrinsic spin? I guess the total spin would be conserved if I had like two such objects, but
right.
If the individual objects, yeah, they would not conserve their individual spin.
That's right.
But I can't really think of them like particles in a way, they're really like, if you mess with the configuration, you'll mess with this quantum number. That's
absolutely right. And in fact, like clearly because Matt, I had, bribed you into asking this question at this stage, I'm going to discuss this next, very much so. So thanks for the question, Matt. Okay, so let me just dive.
We will be discussing like
what happens when they merge together. Yeah. Let's go ahead, please. Yeah, you were asking something.
You're going to talk about formation and what will be the distribution of these objects.
I wish I could. I will not tell you. I will tell you what I think should happen, but I will not give you any quantitative results because we haven't done it. But I will tell you what happens when these objects smash into each other. Okay. So I will discuss it. Okay, so let's talk about implications. So first, let me just remind you that all of these objects, whether it's in the scalar case, vector case, or the tensor case, for a fixed particle number, in the non-relativistic limit, they actually have the same profile and energy density. So as far as gravitational properties are concerned, for these individual objects, you can't tell them apart in the non-relativistic limit. Okay, they just, if density is the only thing you can probe for these individual objects, you can't tell them apart in this limit. However, when you smash them into each other, they can indeed reveal their nature. To give an example, if you smash two of the objects together that have the same spin, for example, let's say they're both linearly polarized. This is a vector case, for example, then that essentially can be mimicked by just two scalar field lumps colliding together, that you cannot tell the difference. Okay? That is, the scalar field configuration can mimic this. However, if you try to collide two of them where the initial spin configurations are different from each other, then that cannot be mimicked by any scalar field configurations that you collide together. So this you can show, at least in the initial stages, you can show analytically, and then thereafter you have to, of course, do simulations to see this. So here is an example of a simulation. This particular simulation is carried out by Rohit Karur, who is a undergraduate student at Berkeley, working with me now at Rice. So on the left-hand side, you're effectively seeing a scalar collision of these two objects. The color scheme is just the density. So you can see that on the scalar side and the vector side, the density patterns that emerge when they collide together are different. And you cannot mimic the vector case with the scalar one in this case. So certainly they lead to different density patterns when they collide. Now, this is an unrealistic case of whether we are going to ever catch two of these objects colliding together or whether we are going to catch them in action. What we want to study is perhaps something slightly more realistic, is perhaps a clump of these objects merging together and see what their final state would be. So we are trying to do this. This is all work in progress, so take this all with a grain of salt. On the left-hand side is a collection of these objects, which is in a scalar field. On the right-hand side is a collection of those objects in the vector dark matter case. And they both have the same initial mass, same initial density of each object, same location. And now I'm going to let them go.
I think you need the music for this.
I do. So you notice that they both merge, they look very similar as they're initially merging, but hopefully at this stage, you're starting to see that there seem to be some differences between the two cases. In the vector case versus the scalar case. The scalar case is on the left, the vector case is on the right. Hopefully you can see that the scalar case seems a little bit more, there are more patterns around it, but there's more interference patterns in the scalar case compared to the vector case. And indeed, when you actually look at this quantitatively, this turns out to be true. So when you collide a lot of these objects in the scalar case and compare that to the vector case, then the vector case differs from the scalar case in the following ways. Let me remove. First of all, the core that forms, starting with identical initial conditions in terms of their total mass and things like that, it turns out that the vector core is fluffier than the scalar core. Moreover, if you look at the interference pattern, that is the structure that forms the halo that forms around the central core, that halo shows a lot less interference in terms of the vector case compared to the scalar case. And heuristically, you can think of it as the vector is basically a collection of three. If you think of the vector case, it is split into three different directions, and there is interference between three independent directions, but not across different directions. Okay? As a result of which, you get less interference in the vector case compared to the scalar one. So this is sort of the heuristic way of thinking why this is happening. And of course, obviously there is spin involved here. So the central object that forms has some macroscopic spin, which in the scalar case, there's no way to define. I want to be extra careful here. When I say spin here, the dynamics actually doesn't care about the spin so much in terms of, it's three scalars evolving independently and interacting via gravity. So you could, however, the reason we can think of spin is because I derived this from the non-relativistic limit. If you want to think in terms of just three scalars, then you could call this some isospin of this object. Okay. So the figure that I'm showing here, by the way, is again work in progress, but it shows you the power spectrum multiplied by k squared for the region around the central core. And you can see that the scalar part has a peak at a larger wave number and is higher in height compared to the vector case, which is what we were seeing visually as well. So this, I think, is an interesting way, hopefully, that in the future we can potentially distinguish them. And here, by the way, the horizontal axis has become kiloparsecs because I've just chosen a particular mass for the dark matter, which is very light. But we can do this for any mass.
Is it degenerate with mass? Like if I change the mass?
Absolutely, yes, it will change. It meaning I guess I should ask, the overall scaling is, if you're asking whether I can reproduce the vectors with the scalars or not, I suspect not, but I can't, I'm not 100% sure because I haven't fully figured that out yet. Like we haven't actually, we are thinking through it right now to make sure that there are no degeneracies where we can get from one to the other with some appropriate scale. That's it. It's a valid question. Okay. The other way you could distinguish these objects from each other. So these were sort of, I was still trying to remain within gravitational context and in the non-relativistic limit alone. Now I want to think, actually, let me just answer one more question that Matt had asked. So when you look at the total spin of these interacting objects here, that overall is conserved. But of course, the final spin, I mean, there is no sense in which the individual object is left over at the end. So there's just a combined spin at the end of the central object and the spin of the halo, if you want. But the individual spins lose meaning for the individual objects that you begin. But the total spin is conserved in this. So how else can we distinguish these objects? One way between these different objects, whether it is between the scalar and the vector case, or within the vector case between different spin multiplicities, or between the tensor case between different spin multiplicities. Another way of distinguishing them is to allow for self-interactions. Self-interactions in the vector case can be somewhat natural when you try to think that you are getting this massive vector field theory by integrating out some heavy Higgs in the system, and that gives rise to attractive self-interactions. You could also, for the tensor case, for the massive spin 2 case, bigravity, for example, has self-interactions already built in. And so if you go beyond this non-relativistic limit, you would have those interactions be present there also. So self-interactions can naturally lift some of the degeneracies here as well. Moreover, you can also lift the degeneracy between these objects by thinking about relativistic corrections, that is going beyond the non-relativistic approximation. So let me just show you a little bit about the self-interaction case. This is work that we led by Hongyi Zhang and Mudit Jain. We did this study for the self-interaction case very recently. This was just submitted a couple of days ago, a few days ago. So for the self-interaction case without gravity, you also have these solitonic configurations. I hope this plays. So now you can again see these two different types of solitons. This is for the vector case, but with self-interactions and no gravity. And you're seeing what the vector field is doing in these two cases. And this one, unlike the earlier part of the talk, this one is actually from full 3D simulations, 3+1 dimensional simulations, fully relativistic simulations. Okay, this is not in the non-relativistic limit. The interesting thing that happens here, apart from the fact that these objects do exist and they are somewhat long-lived, at least about 1,000 of their oscillations, that they are, in that sense, at least they're that long-lived from what we can check. One of the important things that happens is previously both of these objects would have, for the fixed particle number, would have had the same energy. Now, including in the self-interacting limit, we find that they have different energies. And the spinning one has a higher energy for a fixed particle number compared to the linearly polarized object. And with some massaging, you can show that the nonlinear part of the potential can be written in terms of the spin density to an extent. And this term being non-zero contributes partly to the fact that the degeneracy between the two is lifted. So it's a spin-spin type interaction, it seems. And that is partly lifting the degeneracy. Okay. This is sort of just a motivational slide. So here what you're seeing is some work we had done earlier. This is led by Thomas Helfer and Eugene Lim and Marcos Garcia. This is just a collision of two lumps of these objects in full general relativity now, and looking at the gravitational wave signature that might be generated from it. I know that something like this, of course, I think, Matt, if I remember correctly, you had worked on this, about this beating of objects before they settle down, in terms of just phenomenologically, in terms of the signal. I know Nyash has been thinking about echoes and things like that. It was different physics, but similar phenomenology afterwards in terms of the gravitational wave signal. But here I'm presenting this as sort of just as a motivational slide to say that if we are hoping to repeat the same exercise with these higher spin cases with full GR to see how the signature would be different in gravitational waves, both in terms of the polarization of the gravitational waves that comes out and just in terms of the overall wave signal, the waveform that comes out as well. But we haven't done it yet. We are still thinking through.
Does it look like this for a merger event as opposed to head-on, like with this ringing? You get these modes.
So we haven't, so Matt, you might know this already. So we haven't done the in spiral because, just as you might imagine, it takes too long. You're asking about an in spiral versus a head-on one, is that right?
Yeah.
Yeah. So the in spiral one, we haven't done it yet. I think I suspect there would still be some ringing. because these guys don't settle down that quickly at all. We've done some preliminary things, at least Eugene and Thomas have, but I don't have a quantitative answer of how pronounced this ringing will be in that case.
Would we even be able to distinguish the signal, like, or is it like we have to look into a stochastic? Because you're thinking about dark matter, so the masses are much smaller.
Sorry, yeah. So here, as I said, this is the motivational. So here you can imagine that let's say I imagine this made out of m equals 10 to the minus 11 EV.
Mm-hmm.
Okay, in that case, these objects in the very compact case would be, I think, was it solar mass or 10 solar masses, I forget. Okay, so they would be comparable to sort of black hole signals. And you could certainly make them do this in that case, but you have to make them ultra compact, right? You can't be in the non-relativistic regime to generate these signals.
Mm-hmm.
So in that case, it could be black hole mimickers if you want, in that case. And if you make them really compact, you can, in fact, you can merge them and you can form black holes via their mergers as well, directly.
Or black neutron stars or things like that.
Some things like that, yeah, exactly. Like in this case, the parameter I've chosen, it doesn't actually collapse to a black hole. It sort of stays together. If you do if you go beyond a certain regime, they collapse to black holes. If you go even beyond that regime, they collapse before merging also. Okay, oops, right. Here's one more sort of application. Again, this is more motivational in terms of higher spin case than actual results. So this slide, what you're seeing is a merger of two of these objects. These are for the scalar case. And in this case, I'm thinking of them as axions, so I'm coupling them by an FF dual coupling. And what happens is when these objects merge together under certain conditions, even if individually they are not great antennas at radiating away photons, when they merge together, a threshold can be crossed and a parametric resonance instability takes over, which leads to a rapid dispersion of energy of this object into photons. Okay, so they hang out by themselves individually, but when they merge into each other, a threshold is crossed, and suddenly they give off a lot of their energy into photons. So this we have done for the scalar soliton case coupled to electromagnetism. We haven't done it for the vector case or the tensor case yet. Similarly, we have done something similar for the scalar case, and just putting in terms of strong magnetic fields, either be in presence of such magnetic fields could be there for around neutron stars and so on. And again, with this FF dual coupling, you can emit lots of electromagnetic radiation. What would be interesting is to repeat this exercise with this higher spin objects as well, because the spin configuration of this object, again, I think will imprint itself on the signatures in electromagnetic waves that come out of it. In particularly, some spin configurations of these objects are not efficient radiators, whereas others are, just because of the way, like for example, in the non-relativistic limit in particular, this trace part in certain spin configurations, polarization configurations, doesn't give you a time-dependent coefficient here, whereas in others it does. So it really can influence whether you get a lot of radiation or not from these cases. But again, this is work in progress. We are, or rather thinking in progress. We haven't even started working on this. We just have written down what could potentially happen. Okay, so Ghazal, you had asked me about formation mechanisms for this. Okay, so here I'm just showing you the formation mechanisms that can take place for these objects. For the scalar case, on the left-hand side is the full three-dimensional simulation for the where self-interactions are strong. On the right-hand side are examples where you form these objects out of by purely gravitational interaction. But again, this is for scalars. For the vector case, I don't see anything significantly different apart from two things. One is that the initial conditions will be different, most likely. But otherwise, I suspect we can repeat these calculations here, what people have done before, just instead of thinking about one object, we have to think about three equal mass objects starting off together. but work that remains to be done, this still needs to be done. The other thing that will be exciting and different is, for example, in the vector dark matter case, there's been interesting work in terms of production from a misalignment-like mechanism in the early universe, which picks out a characteristic scale in the power spectrum. This is on small scales, and you could get a peak in the power spectrum at small scales in the initial conditions. But that could also manifest itself in the later dynamics. Moreover, that mechanism also tends to favor one polarization over the other when you produce them. So that could also lead to interesting effects in terms of what kinds of objects can form in here as well. So I think, again, maybe it's just because I've been working on this for the last 2 papers, but I'm quite excited about where this can take us and what kinds of interesting phenomenology can arise, which really hasn't been explored yet at all. This is sort of that, a slide with all the things that we could think about that you write at the end of a paper, but not having actually worked through everything, which is, I just mentioned about the different things you can do by just thinking about the spin of dark matter. You could do everything you've done for scalars and light scalars, and you could repeat this for vectors and focus on the spin and polarization aspect of this. Whether it be, some of this has been done, of course, super radiance parts of this. You could talk about, for example, direct detection. Direct detection in particular, when you couple these vectors to, if you allow it to couple to baryons directly, then the direction of the vector field, more specifically the polarization, can lead to accelerations in your test masses that are dependent on the polarization of the field and the directionality of the field. So that could be an interesting thing to look for as well. Okay, I've spoken for too long. Let me just quickly rush through my summary slides. I've told you about light, highest spin dark matter, and some interesting effects in them. I've shown you that the non-relativistic limit is just a multi-component Schrodinger-Poisson system. This can help in simulating these systems and understanding analytic properties. I've told you about some fun solitons that can arise, in particular solitons with macroscopic spin. These things can be distinguished either by the interactions with each other or based on the end states that form or halos that form, or by including things like self-interactions or relativistic corrections. And I've also told you, not quite in complete detail, but just in a broad brush way, the types of observational implications that could arise, particularly focus on the fact that the polarization of these higher spin objects or just higher spin dark matter can play a role in the observational implications for these things. All right, thanks a lot.
Thank you. Can use your electronic hands or visual hands. Very nice talk. I really enjoyed it. Please go ahead, ask your questions from Mustafa. Anyone? Feel free to turn off your microphone if you want to ask.
By the way, I should also mention, I forgot to, if you may permit me, I also wanted to advertise that we have a postdoctoral position available in the group. So if anybody who's listening here is interested in the types of things I discuss or in reheating, which I did not talk about at all, please feel free to apply. All right, go ahead.
So in terms of observational prospects, I mean, I don't, where should we look for this?
So observational aspects, if you want to look, so let me start with direct detection. So for direct detection, people have already looked for, of course, dark photon, dark matter. They're looking for it already because it will lead to accelerations, direction-dependent and polarization-dependent accelerations in your test masses. So people are looking for that with LIGO-like detectors. You could do this. Or you could do it with DM radio type detectors that are looking for axion photon conversion. So that's a direct detection.
What can you do with LIGO? Can you?
So LIGO, remember, like it's I mean, at the end of the day, it's just trying to measure how your masses are shaking a bit. So if you have an extra force where you couple these fields to the baryon number, it will cause an extra force on these objects. So, and that force might have a directionality to it because it depends on the direction, potentially depends on the direction of the field, because now you have a vector field, not a scalar. Okay. So that's one way to think about it. In that case, if now furthermore, if these objects, so that's just talking about dark matter without thinking about solitons. The solitons would add an extra event rate or extra amplitude of the field if it passes through the detector as well. Then we can start thinking astrophysically. So if you want to think astrophysically, one way of thinking about it is, let's see if, in principle, again, I'm going to be a little bit broad here first. In principle, you could imagine that the distribution of density and the interference pattern in halos will be different for these vectors versus a scalar case. So that's, if we can probe the density distribution, that could be one way to do that. So maybe via lensing, maybe via substructure. That could be one way to look for this. If you now allow for couplings of these objects to, let's say, electromagnetic fields, okay, this is a little bit, it's an extra bell and whistle I'm adding to it. In the scalar case, of course, FF dual is a natural thing to do. Here also, you could create a similar coupling. But in that case, if you see flashes of light from these objects merging or interacting with each other, then perhaps the polarization pattern from these objects could also be revealing about the polarization state of the object itself. Same thing holds true for gravitational waves from collisions of these objects. That's another place where. So all of these things I could imagine doing. And the other things people have already thought about, Nyash, which you know better probably, is thinking about super radiance and things like that. Higher spin things can have an effect there as well.
So I guess I'm just along the direction of direct detection. So I guess if we're looking for these are like axion detection experiments that we are thinking about, right?
So that, yeah, absolutely. Yeah. So axion detection is another, that you could just adapt the axion detection experiments for these dark photon things. And people have already done that. This is not we're not saying anything new here. People have already been thinking about these higher spin dark photons in particular, and trying to see if they can constrain things with what they're doing with axions.
Yeah, I guess what I was thinking that in some direction you could work further along is in terms of, I mean, the substructure on a small scales do impact direct detection experiments, because we are flying through structures. So we probe basically substructure on very small scales. So if there are certain properties like this power spectrum on a small scales, that would be different for these different microscopic models, then we could basically think about direct detection experiments and how they kind of the temporal variations of the signal. That could be something one can think about, because that's kind of in some sense the highest resolution probe of dark matter that we have is just flying through them, right?
Absolutely.
Yeah, so that might be an interesting direction.
No, absolutely. I'm actually like just the buzzword that you mentioned, right? Like just ultra small scale structure in dark matter is exciting. It's interesting. That's where I think all the interest, at least for me, that's where the distinguishing features are. We all know how dark matter works on very large scales. It seems to be working as dark matter should. But to distinguish different ideas, it has to be on the small scales. And it does seem like these higher spin things do have effects, particularly on small scales that are different. On large scales, we can't tell the difference. Okay.
Right.
So it certainly seems like we should look more in that direction. And yeah, if you have more ideas about what we could do.
Yeah, there is this thing people used to talk about more as this dark matter astronomy, where we kind of could talk about the small scale directionality of dark matter. I mean, I think it's very much context dependent. I mean, whether like for WIMP it would be something different than for axions. And I mean, we used to, I mean, we did some papers with Ed Bertschinger a long time ago for WIMPs, basically. If you fly through them, how your signal changes with time, and that tells us about a small scale structure. And I mean, for of course, for these models, you could ask the same questions.
Absolutely.
Mhm.
Absolutely.
Okay,
But,
cool.
yeah, I remember you guys doing it. I was a postdoc then.
Yeah, yeah, I remember that. Yes, indeed. Yeah, cool.
Any other questions? So just to clear my head, so if I'm thinking about this, as a dark matter candidate, this would be predominantly, most of the dark matter would be in the soliton part of the solutions, or like mix of the rest of the field in other configurations. And
I think the truthful answer is I don't know, because it depends upon the formation mechanism, like how the initial conditions start off, how much of the fraction you will end up in solitons. If I go by what is known for the scalar case, then only some fraction will be locked up in solitons. Okay, it will always be a mixture. You can't make everything into solitons. It's tough to do that. But I can't give you a quantitative answer, because it does depend on what initial conditions you start off with. In this case, if you start off with something that's highly misaligned, so that the nonlinearity can form solitons earlier, okay, then that's great, because you could end up with quite a few of these. But if you just allow for usual structure formation to take place, then you will only get these objects in the densest regions, in the cores and things like that. So then it's less likely that you will have most of the dark matter in terms of these solitons.
sounds good. Any other questions? Okay, looks like everybody had their questions, and we passed the hour. Thank you, Mustafa, again for accepting our invitation. It was great having you. Hopefully we see you in person very soon sometime.
Absolutely.